Welcome to the second lesson about transition metal complexes. Today we're going to have a look at the geometries or shapes of transition metal complexes. I've put a note there saying that you can't predict these using VSEPR theory. There is a way to predict them, but we can't really do that with knowledge that we have at A level. You do need to know these four shapes, and you need to know one or two examples of each. But for today we're just going to really make sure that we understand several of the key ideas. So last time we talked about coordination number being the number of dative covalent bonds or coordinate bonds that are present in a complex. So for an octahedral complex there's going to be 6. Remember that sometimes can cause some confusions for people, oct being the prefix for 8. But we've only got 6 dative covalent bonds in there. That's because the shape that is formed, the three-dimensional shape that is formed by this complex, has 8 sides, so hence the reason it being octahedral. So, if I do a nice simple example of a complex with unidentate ligands that has the octahedral geometry, it would be the hexa-aqua copper 2 ligand. So the hexa-aqua copper 2 complex. So remember last time we spoke about ligands as being species that have a lone pair that are able to form dative covalent bonds to copper 2 plus ions, or in this case any transition metal ion, but in this case it's a copper 2 plus ion. And this whole species here is a complex. We've got ligands, dative covalently bonding or coordinate bonding to a transition metal ion. We technically should put these all obviously in a square bracket. I'm not going to bother doing that for the moment. We're going to deal with bidentate and multidentate ligands in a little bit more detail in future lessons. I've just included them here just so it's a sort of taster of what we're looking at, and I'm going to show this with the 1,2-diaminoethane ligand. So in this case I've got, or I will have, 3 1,2-diaminoethane ligands complexed, dative covalently bonded to the copper 2 plus ion. Notice that the coordination number is still 6. We've still got 1, 2, 3, 4, 5, 6 dative covalent or coordinate bonds. The bond angle for, or the approximate bond angle for octahedral complexes is 90 degrees. Now we could draw these in 3 dimensions with using dotted lines or hashed lines back here to show that these go back into the plane, and wedges coming out of here showing that they're coming out of the page. It really doesn't make that much difference as far as the AQA exam board is concerned. They're okay with us drawing it in a more simplified fashion because it's a little bit quicker and easier, as long as we write the bond angle next to it and write the name of the shape next to it. So that's the octahedral geometry. The tetrahedral geometry. Coordination number of 4 and an approximate bond angle of 109.5 degrees. I'm going to give an example where we've got 4 chloride ligands dative covalently bonded to the manganese 2 plus ion. So a coordination number of 4 because we've got 1, 2, 3, 4 dative covalent bonds or coordinate bonds, and an approximate bond angle of 109.5. Again, I haven't drawn this in 3 dimensions, but if I write next to the shape that it has a bond angle of 109.5 degrees and it is tetrahedral, then that's fine. We're going to have a look at another complex now, which is this one you do actually need to know. I'll make sure in future lessons that I'll make that quite explicit. But this is the square planar geometry, and the example you need to know is an anti-cancer drug called cisplatin. And cisplatin has two ammonia ligands and 2 chloride ligands dated covalently bonded to a platinum 2+ ion. So this is called cisplatin. There is another isomer called transplatin, in which case we'd swap this ammonia ligand with this chloride ligand, but we'll deal with that when we look at isomerism in transition metal complexes. Again, we don't need to draw it in 3 dimensions, as long as we write next to it the bond angle and the name of the shape. The last shape we need to know is a linear complex. It has a coordination number of 2 and a bond angle of 180 degrees. An example, again this is an example that we need to know, and this is the diamino silver 1 complex, which has 2 NH3 ammonia ligands coordinate bonded, dated covalently bonded to a silver 2+ or a silver 1+ ion. So there's going to be some questions for you to have a look at, but before that I need to give you a little bit more information, just to increase the variety of the number of questions that we could answer, and so that you can apply your understanding to unfamiliar situations. I'm just going to introduce some new ligands. You don't need to know these ligands, but I'm just going to give you the information so that you can use them in the question. We've got a fluoride ligand, very much like a chloride ligand, is a unidentate halide ion with a lone pair of electrons. Then we've got this carbonyl ligand. It's a neutral ligand. It's a carbon triple bonded to an oxygen, and the lone pair is located on the carbon atom. And then we have a cyanide ligand, which is a Cn- ligand, so it's negatively charged, and the lone pair is located on the carbon atom. So I'm going to now do a one worked example for you before I put the 10 questions up that I want you to have a go at. So I said for each of these questions I want us to draw the structure and you to work out the charge of the transition metal ion in the complex, state the coordination number, and then the approximate bond angle. So here is our complex, NiCN 4 times 2-, and we're told that it is a square planar complex. So I'm going to put a nickel atom in the middle, and I'll work out the charge in a minute. I know it's square planar, so I'm going to draw this geometry, and it's using a cyanide ligand. So it's square planar, so the bond angle is going to be 90 degrees between the CN and NiCN bond angle there. The coordination number is going to be equal to 4 because there are 1, 2, 3, 4 dated covalent bonds. And then we're going to work out the charge on the nickel ion. We have got 4 times cyanide ions present. Each cyanide ion has a charge of 1-, which means the total charge due to the 4 cyanide ions is 4-. And then the complex itself has a 2- charge, which means that the nickel ion, in order to balance that up, must have a 2+ charge. So we can put nickel 2+ there, and I can put nickel 2+ there, just to complete the information. Notice, obviously it looks a bit confusing because I've used Cn in 2 different examples here. C.N. I'm using to abbreviate for coordination number, and Cn- is the cyanide ion. So there are going to be 10 questions for you to have a look at. If you haven't got the sheet, I'm going to pause for a moment so you can look at those, and if you want to pause the video. And then here are 4 more. So, and if you want to pause the video and then I have some answers. So the answers for the first 6 examples are here. If you want to pause the video, and then the answers for the last 4 examples are there. So, having done this activity, it will be worth us trying to summarise this because you need to learn it. So, if you have been able to print the worksheet out, then here is a summary sheet for you to fill in. And then I'm just going to put the answers to this summary sheet up. So there's the answers to the summary sheet. Having done this, it's really important that you try and repeat this maybe once every 2 days so that this information becomes really secure in your long-term memory. Thank you very much.